course, it's my great pleasure to share with you some of the work we've been doing over the last couple of years. And at the end of the day, I would like to convince you to some extent that the future is not necessarily AI or pure AI. I do believe in certain applications we need to think about combining the state-of-the-art of our deterministic methods, benchmark methods, with AI. And this is what I would like to show you today. So in short, my presentation will go through motivation and objectives, and I will talk a little bit about the principle of reinforcement learning, and particularly inverse reinforcement learning, and where this might be of interest for us. And I will talk about the methodology and case study we have been looking at, and of course I will show to you some results, and I will finish with the conclusion. So the whole challenge is to teach an agent how to follow a pathway, and this is what we will see together today. So most of the problems encountered in the development of autonomous plants and devices and cars involve necessarily the development of optimal pathways, which will also include or involve optimal tracking control problems and their uncertainties. This is very interesting because most of the problems encountered in pharma also, they may have trajectories, and this is typically the case of crystallization, where we are interested to follow a pathway in the solubility curve. For example, we would like to avoid a secondary nucleation. If we have a seeded process, we would like to control the supersaturation level, and this is typically what happens. We have a pathway we would like to track and control effectively. The biggest question again here is, do we really need to develop AI? Are we happy enough with the MPC, for instance, control strategies? And does it mean if we go for AI, does it mean we have to rule out the MPC? The answer to this is not necessarily the case. We may need to use the MPC to teach or to train our AI, and this is what I will show you. This will help us reduce the training cost and, of course, generate some useful data for our agent. So in short, what we would like to achieve is, of course, to develop AI-based self-optimizing control strategies for pharmaceutical manufacturing. We would like to deliver robust control strategy. That means we have to address the case of uncertainties, and this may happen due to the model uncertainties, which is quite common, but also due to the measurements. We will be also looking at plug-and-play control strategies. That means we would like to develop transferable and portable control strategies that can self by themselves. And at the end, we would like to develop new control strategies by combining the benefits of both MPC and AI. And of course, this will happen under the condition that we will be able to deliver effective training strategies. So I don't need to probably spend a lot of time talking about the different strategies for AI. We have seen already excellent examples delivered and presented by Professor Hurst and by Maxime, and I'm pretty sure the next speakers will tell us a little bit more about the supervised and unsupervised techniques, which will mostly use, for instance, SVM and Monte Carlo trees. So the problem in this particular case may be, for instance, a classification. That means we need to feed some label data, and we would like the algorithm to do the same thing for other data that has not been used during training. We may be also interested in clustering, but in our particular case, we are interested in reinforcement learning. Essentially, reinforcement learning is a Markov decision process, which will require a stochastic optimization strategy. In our case, we will be using deep learning techniques, and this is how it works. The problem is based on the design of an agent, and the agent will observe the environment. Here in our case, for instance, we have a crystallization process, which may be the real process. That means we have to generate loads of experimental data, or alternatively, we can use a mathematical model. So how does the agent learn? The agent will come up with an action, so it will act on the environment and then observe what happens to the process. And based on the observations, the agent will receive either rewards or penalties. And this is, you may agree with me, this is how our kids learn, by penalizing them. Of course, this is the old school. We don't want to go that way. But of course, this is how children learn. And of course, after many iterations, the agent learns. And at the end of the day, what we are interested in is the whole episode, which means a whole run or a whole simulation process. And after a certain time, of course, the agent will learn and will deliver, hopefully, what we would like it to deliver. As I mentioned earlier, the environment can be the experimental process or a very good representation of the process, a mathematical model. Of course, you may argue that the model does not capture reality, and this is why we need to look at the uncertainties. So how does it work? Over a certain number of episodes or simulations or experimental runs, the agent will learn, will undergo certain exploration and exploitation, and at the end of the day, it will deliver what we need from it. And once we are happy, we save the features of the agent and deploy it in the real world or in the simulation world. So what happens now if we have or we would like to use the MPC as part of the training? Of course, the MPC is one of the state-of-the-art control strategies, and no one would argue that the MPC is not good, but the whole idea here is to use the MPC as an expert to train the agent, in which case we would like to shorten the burden, the training burden, and help the agent learn from the MPC. So essentially, the agent will be observing the MPC controller, and it will try to mimic its actions or its actions and the outcome. So it depends on what we would like to achieve at the end of the day and what are the resources available for us. Once the agent has been undergone the right training, at the end of the day, we will be implementing the agent in the real process or in the mathematical model of the process. So what's the methodology we've been implementing? When it comes to implement the inverse reinforcement learning, the first thing is, of course, to develop a mathematical model. At Loughborough, we have strong tools to improve our mathematical models, such as estimability and identifiability. We are confident that by implementing these techniques, we can develop a good compromise in terms of reliability and precision. Once we have the mathematical model, we would like to identify our optimal trajectories. And of course, once we have the optimal trajectories, we would like to develop the reinforcement learning around these trajectories. That means we need to design the architecture of the inverse reinforcement learning agent, design the reward functions, and this is something really critical in this context, and I will tell you a little bit more about it. And of course, we train the inverse reinforcement learning agent, and then we go through a certain number of tests to make sure that the agent is fully satisfactory. Again, this is our process. We are interested in tracking 3 optimal trajectories: the cooling trajectory or the temperature trajectory, the supersaturation, and of course, most importantly, the crystal size. So how does it work? Again, the agent will observe the MPC, and the MPC will act on the process by changing the cooling rate, and the agent will be sitting there just to learn without acting on the process at any point. Once the agent has been trained quite effectively, then we deploy it, and if we are not happy, potentially we can go back, redesign, and retrain the agent. What happens now if we have to take into consideration the real world problems? That means we have to capture uncertainties, both on the measurements and the mathematical model, and this is what we will do at the end. That means we have to train and validate the agent under uncertain environment. Of course, this is typically how the mathematical model looks like. We picked up a very simple case. This is a cooling batch crystallization, and we use the standard method of moment. We have only growth and nucleation, but currently we are looking to more challenging process involving 2-dimensional population mass balance and anti-solvent crystallization. So again, this is the mean particle size, and we would like to follow a certain number of trajectories. And with this model that we are confident that delivers what we need from it to some extent, we implemented an optimal control strategy, a dynamic optimization control. That means we can identify how to cool down the process and what would be typically the supersaturation trajectory, and of course, the crystal size trajectory. You may think that at the end of the day, we are more interested in the final particle size, but in reinforcement learning, it is also critical to keep our system under control over the whole trajectory to make sure that we will avoid deviation. This is particularly important for to avoid batch-to-batch variation in industrial problems. So, in terms of architecture, we have different ways to design the reinforcement learning agent. And of course, we have different alternatives. People believe, for instance, like that deep deterministic policy gradient are really interesting because they will be using what we call an actor and critique networks. That means you have within the agent itself, and another agent observing and looking at how the agent works. In a way, like you may think about it like a minister and a shadow minister, someone looking how the agent works, and it will evaluate the action of the agent and help the agent get some feedback. And of course, the reinforcement learning involved stochastic optimization, and we are using stochastic gradient descent with momentum. Of course, there are other alternatives. And what happens at the end of the day, we need to train the agent, and what are the key performance indicators we are looking at is, of course, first of all, we need to maximize the rewards. And if we are using penalties, we would like to minimize the penalties. Here, for this particular example, the best case scenario would be to achieve 0. That means 0 penalties. In addition, we would like to minimize the cost of training, minimize the time and the number of episodes, the number of runs. And from optimization perspective, we would like to have enough exploration. That means we would like to avoid local minima. And once we have the exploration, we move on to the exploitation to get the best value in a better accuracy. So, of course, at the end of the day, we need to see that the reinforcement learning agent delivers what is expected, and this is where we need to look at the validation and see whether it performs or whether it follows the reference trajectories quite effectively. Okay, so the first question we have faced initially is how to design the reward function. We have 3 alternatives. The first one is to combine rewards and penalties. That means if the agent will achieve or will be within acceptable range, we will give a reward. And if it is outside to some extent, we need also to specify the range, we can put a penalty. Alternatively, we may think about just rewards and ignoring the penalties. And at the end, we can also look at the penalties only. And in the literature, people believe that using penalties is the most effective way. So we wanted to double check whether this makes sense or not. And to see it better, usually you need to validate the agent. So overall, this is what we have implemented. And I will show you typically what happens if we use these different strategies. Of course, the number of episodes, the number of training sets of data depends or changes from one case to the other. And this is typically what happens. And after validation, we thought, after many different cases, we thought that using penalty only is the most appropriate way to train the agent. What happens now when it comes to put the reinforcement learning agent into an inverse reinforcement learning? Again, what is typically a inverse reinforcement learning? It is typically an apprenticeship reinforcement learning. That means you have an expert and you have the agent learning from the expert without really acting on the process. So that means we need to minimize or to keep track on the expert action and the agent action, and we would like to minimize these. Alternatively, you may think about minimizing the deviation between both actions, the agent and the expert, but also the outcome. But here, again, to minimize the training burden, we looked at only minimizing the actions. And of course, we thought about transfer learning, and I will come back to this in a moment. So this is what happens with the training by using both a PID and an MPC. Of course, the PID has been around for more than 80 years, but it is still relevant to industry. But of course, the MPC is considered as the state of the art for process control. And this is what happens in terms of training. Surprisingly, and this is something we are not necessarily sure about, training the agent using a PID expert seemed to take much longer. This might be due to the fact that the PID is suboptimal in terms of control. However, the MPC is already, better in terms of performance, and this helps the agent to get there very quickly. So, in order to improve the agent, there is another strategy called transfer learning, and we believe that transfer learning is extremely important in terms of allowing transferring any control strategy or even transferring a mathematical model from one context to the other. So how does it work? Simply by breaking down the problem into different levels, starting, for instance, by training the agent with respect to the temperature profile, then increasing difficulty by adding another profile, such as supersaturation, and at the end, combining all the three at the same moment. Of course, you may think about multi-objective optimization, but this means also we have to take into account weights. So what happens now if we put this into the context of inverse reinforcement learning? What we have done, we trained the agent, the inverse reinforcement learning, using typically what the MPC is able to do. And once we have saved the features, we took the inverse reinforcement learning agent and trained it again to improve its features. And I will show you what happens by doing this. So in terms of simulation results, this is what happens at the beginning by implementing the inverse reinforcement learning versus PID or versus MPC. And qualitatively, when we think about it, and this is particularly the case of particle size, all of them seem to perform as well as each other. And if we zoom in, it looks like the deviation is not that high. But if we are interested in more qualitative insights, we looked at the sum of the squared errors, and this is where we start observing some deviations. But overall, we may think or we may see that the inverse reinforcement learning agent performs really well compared to the MPC. And this is a bigger picture where we take into account the crystal size, supersaturation, and process temperature. And again, overall, we may think that the inverse reinforcement learning agent is extremely satisfactory. Now, what happens if we implement the transfer learning, and this is what is being highlighted here, surprisingly, we see that the agent after transfer learning has got the potential to outperform the expert. And this is an extremely important thing. That means we can extrapolate or transfer our reinforcement learning agent into a different environment, and by a relatively low training episodes, we can achieve potentially better performance. Of course, all depends at the end of the day what is the most important trajectory for us, but here obviously you may think that the particle size trajectory is certainly the most important, and this is what I was trying to refer to. These dashed dots here are associated with the inverse reinforcement learning plus transfer learning. Now, what happens if we take into account uncertainty? Because models, as we all know, are not necessarily, they do not necessarily capture reality, and we need to look at what happens if we include measurement uncertainty and model uncertainties, and this is what we have implemented by putting a Kalman filter within the reinforcement learning framework. And we looked at different levels, and here I show you 10% measurement noise and 10% deviation in the kg, the growth rate parameter, and the nucleation rate parameter. So overall, again, we see that despite this level of uncertainties, our reinforcement learning agent seems to perform really well. Of course, this requires further investigation experimentally, and this is what we are really interested in. We will be much more than happy to, if there is anyone interested in bringing this to more experimental applications. So to conclude what we have done, we have implemented a model-based reinforcement learning controller, which was designed and trained to address a tracking control problem with 3 trajectories. And we have used a deep deterministic policy gradient algorithm, which seems to be one of the most effective ways to achieve reinforcement learning. We looked at 2 expert controllers, PID and MPC, and we have developed a transfer learning technique to improve our reinforcement learning agent. And at the end, we looked at robustness. That means we put everything into the context of uncertain environment, and overall, our inverse reinforcement learning, using a Kalman filter and using the transfer learning, our agent seems to perform really well. With this, I would like to thank Paul Anandan, who developed the simulation, Chris Riley, who co-supervised the project, and I'm really thankful to the whole Articular team for their long and very insightful discussions over the last couple of years, particularly the out-of-the-box discussions that led to a lot of insights and, of course, led to these achievements. Thank you very much indeed.
Yeah, so today, there was a big choice of different things to talk about today, but we plumped for solubility prediction because this has been going for quite some time now. It's a more mature bit of work. And I've tried to focus this on the more easily abstractable learning. So if you don't deal with solubility, don't worry too much. Most of the slides I culled were in the background, so I'm going to be very, very quick. In the arena of solubility prediction, in my head, I just split it into two camps, and these are just my terms, not standard ones, mechanistic models and data-driven models. And basically, mechanistic models are anything that has come from a human brain studying science. Usually, they all go back to your laws of thermodynamics, and they tend to have some extra parametric component to refine the predictions for solubility. And many have been around for a long time. There's still more coming out. They're constantly being improved and optimized. If you've dealt with them, you may have heard of these ones that I've put here, UNIFAC, SAFT, and CosmoRS are very prominent ones in the industry. There are more. There are plenty more. But the parametric component is the bit I focus on here, because they do need some kind of input to give you an output. And if you don't have that input, you're stuffed. You can't get a prediction. Game over. And for someone who's more on the machine learning side, which is, spoiler alert, the other half of the slide, that's important, because if you don't have any number, you can do nothing. Whereas if you've got even a bad number, you can work with it. Which brings me nicely to the data-driven models, and I just sum that up as anything that doesn't have a rationale based in science and thermodynamics. It's purely something you have fitted to some data, and it comes with the hazards of it's limited to the quality of your data. The methods you use to apply it, I mean, increasingly now it's near universally some kind of machine learning approach. And something I've spotted that if you look at the literature on solubility prediction, there's a lot of focus on aqueous prediction. I think that's purely because there's a lot of aqueous data available. Ask anyone in machine learning, more data is an easier time for everyone. But even if people have strayed into looking at different solvents, they do tend to look at them individually. Again, probably because they only pooled enough data for one solvent to look at. And there's obviously a lot more to talk about in this background, but I don't think everyone's a solubility nerd. So I'll jump straight to what we did and the important sides of it. We wanted to buck that trend and look at lots of solvents, because that's what you do in pharma. You tend to want to predict something in predict the solubility in lots of different systems and then make some kind of decision. To that end, we thought, right, let's go out there and try and get as much solubility data as possible. We've heard about the limits of just pooling data from literature, absolutely bang on, and I think we've flogged this horse as much as we can, you'll see. The dataset size we ended up pooling is pretty modest, I would say, 700 data points. It's not tiny, but it's difficult to get more and more and more. But we did that. Those 700 points span across 75 different solutes and 49 solvents. So if you imagine that matrix of points that we do and don't have, it's about 80% sparse. That's the kind of data set we're working with. And from there, right, let's go and predict some solubility. Let's do a mechanistic prediction. We chose CosmoRS for purely pragmatic reasons, nothing else. Then let's do a data-driven prediction. We chose Random Forest, again, a pragmatic choice, happy to talk about if you're interested in later. And then we investigated a hybrid prediction using both of them. And this was another way I culled 20 minutes off this talk. There's the results. CosmoRS is okay, and it is used in industry as one of the more prevalent options for predicting solubility, but across a wide data set of drug-like compounds and a wide range of solvents, its performance is pretty variable, and that's a fair comment, I think. Then our data-driven approach, which I will happily admit was quite crude, to be honest, but it still beats it. And probably the least surprising result of all, if we combine both of these together, we get a better result than either of them in isolation. To me, that's quite intuitive, which is why I've skipped over it, but I'm very happy to show you all of that. Come to my poster later if you're interested. The bit I wanted to focus on is probably the slightly more novel, weirder, more interesting side, which is because we've varied the solutes and solvents, we've got a unique opportunity to triangulate and see, well, if we know what happened here, will that help us predict this completely unknown system? And that's what I'm going to show you here. So this is just an example case to illustrate what I'm talking about. One of the compounds in our data set, we had 20 different solubility measurements. So it came from GSK. GSK had measured the solubility of this thing in 20 different solvents. So if I kept some of them aside, I picked 4. I literally just thought like my undergrad chemistry and picked a range of solvents, polar, non-polar, in between. That leaves me with 16 other solubility points to test against. Now, what happens if I train a model that has never seen this compound before, which is a very common scenario if you're working with a new API and you've got no data on it? Then what happens if I introduce one solubility measurement that's come back from the lab or someone's produced it somewhere along the way, and then repredict all the same points? Then introduce a second one, repredict, and see what happens as the model gains information about this specific API. And look what happens. I mean, this is just one case. Coming up is the response to that point, if anyone's thinking it. The blue points there, Cosmo RS, just to demonstrate it's not very good. That green line is a log unit of error, so it's pretty far out. And then the initial prediction, it's a bit of a gobble up there, but basically dark red is most prior knowledge, lightest red is least prior knowledge. You can see the solubility points shooting straight up towards that grey line, which is a perfect prediction. Fantastic. And I think it is worth highlighting. That means you didn't need that much prior knowledge to really refine the predictions of all your other systems. We only needed 2 or 3 points, and we're really in vanishingly small errors now. Not vanishingly small, but nearly a log unit of magnitude difference. And then, yeah, right, that was just one compound I picked, I claim, at random. It was, but maybe you don't trust me. So what about every other solute in that data set? What about every set of solvents? I picked 4 out of 20. I could have picked a different 4. What would happen? Also, for any set of 4 that I picked, what happens if I chuck the other one in first? That's a lot of different combinations to investigate, and if you're a programmer, that's just a bunch of nested for loops and a powerful computer and time. So we did that. I checked everything you could possibly check. I did the maths. It was about 170,000 models. That's the reason we stuck with random forest, because that's quite quick to execute. And this is how, I think this is the easiest way to demonstrate the result of that. So first, here's Cosmo RS for that entire data set. So you're looking at it in the log space. That diagonal line is a perfect prediction. Those green tram lines are a log unit of error. So really quite a wide scatter of performance. And I've noted there it's deterministic in that that's as good as it gets. That's the number you get and you're done. If you want to do anything with that, which we are, you've got to do it yourself. Now, here's the next one. Now, this is when the model has not got any prior knowledge, so it's never seen that API before. All you're looking for is these points converging on that diagonal, and already that's looking much better. The larger errors are at the lower end of the log space, where it's got a lot less meaning than at the higher end, so this is already a much better performance without having seen the API before, which is worth underlining. Then the fun and games begin with all those combinations. So now, every conceivable combination where a model has seen an API once and once only, make the same predictions for all the other points, and aggregate those results so that you don't look at a bazillion points. You're looking at 1 point per system. The point is the mean that you're looking at. So there is a little variance associated with each point, but I spared you that. And I don't know if you saw it, look at the points moving towards that diagonal. And then if we have 2 points of information, they go further, they go closer and closer and closer. So I thought that's a good way to demonstrate this is a model learning from knowledge that you're bringing back from the lab and adding to it. It can refine, and this is quite straightforward to do. I mean, on the combination, all the combinations are a bit of a, well, it makes your computer sweat, but it's if you've got the code, it's fairly straightforward to run. And there's it all summarized there, and some extra numbers to convince you that this is legit science. I've not seen a single error presented today except mine, so we almost made it, apologies. But yeah, I think the story is quite straightforward. The more data you've got, the more you can shovel into your model, the more relevant that data is, the more it can really lock on to whatever you're trying to predict and give you a good prediction, which is what we're striving for in solubility, and never quite have a good one that's good enough. Now, yeah, I've kind of blitzed through that to get to a conclusion because I think you can abstract quite a lot from that. I underlined it before and I will say it again, like a single solubility measurement was enough to improve it. That's really good. So I'm not saying I can predict fantastically after you give me 40,000 results. I'm saying, like, you don't need that. You don't need much information to improve on CosmoRS, which is an industry standard model. I will be clear, I've not tested any others. So if you're sitting there with your own mechanistic model, this does not apply to you. More data helps more, which wasn't necessarily true. It sounds obvious, but it could be that the model stops learning, or it could be that you're not providing more useful information than you had before. But you could see it was continuing. It was converging. The improvement was slowing a bit, but this is with a very small data set. You could do a lot more with this. Also, that case of zero prior knowledge was still better than what we had before. So it's a pretty low-risk implementation if what you're working with before is CosmoRS. And yeah, I think about it. I mean, obviously, in telling people to change the way they work is difficult, but you can see this would work best if you're iterative with your screening rather than doing one big high throughput. If data's coming back in dribs and drabs, it can constantly refine and refine and refine and improve the predictions, excuse me. I also, I described this as a framework for predicting solubility because I wanted to emphasize all the bits and pieces involved in this, and I think this is a useful way for everyone to think about all their modeling. To get the Cosmo prediction, we required inputs X and Y. In this case, a solvent, in this case, the molecular structures, which we always have if we're working with a molecule, and the calorimetry. Worth noting that limited the size of our data set because we had to get that as extra experimental points. If you change from CosmoRS, those inputs will change, which means you might have access to more data. Then that prediction became an input for the hybrid version of the machine learning. And next to that was molecular descriptors for the solute and the solvent. To me, it's irrelevant which one we used. It was MOE, but I've tried it with different descriptor sets and you get near identical results because there's nothing particularly profound in any one of these sets. They're all just descriptions of molecules cumulatively. And of course, the experimental solubility data. And in my head, these are all little modules and you could pop them in and out and you can change them as you want. And I think this is the way to think about solubility prediction. Any mechanistic inputs you can bring in, they're basically fantastically powerful descriptors. Get them. If you can get CosmoRS and SAFT and UniFac, bring them all in. Some kind of description of your molecule, because that's what you're predicting with solubility. It's based on the two molecules. That doesn't have to be descriptors. It can be, with the advent of deep learning, we've got a lot more sophisticated versions of molecular descriptions than just these old calculations that have been around for decades. It would be cool to try all of this with some of those. And of course, the big one is the training set, the experimental data. This was done with 700 data points pulled from the literature. And it's worth saying, you can see, if I flick back, you can see some of these points that are stubbornly not moving. The model is not improving them, and they're way out from what the model's predicting. I've checked a handful of these, and you can see the culprits at the top there that aren't moving. At least one of those was transcribed wrongly. It was 1,000 times too small. That was probably my fault. One of them, we got the number correctly, but looking at the rest of the numbers in that paper, it was orders of magnitude larger than every other number. I suspect the people who wrote the paper typed the number wrong there or used the wrong units or something. There's probably a little story like that for a lot of these points, which says something about data that you're pulling from the lit. So if you have, I don't know, your own industrial-sized solubility data set that you want to work with, that will be transformational for this. And the algorithm, unless you want to do that drip feeding thing where you need to do hundreds of thousands of models, you're not limited to random forest. You can change that for something much more sophisticated. And that's what, if I was to do a round 2 of this, that's something I'd be looking at as well. Finally, how does this compare to other works? It's worth pointing that out. The performance, if you look at the errors, it's in the same league. In fact, if you've got some prior knowledge, it goes right down. It goes to half a log unit, which is a lot better than half of a whole log unit if you know your logarithms. And it does so with a fraction of the data because we're working in a much larger domain across solvents and across solutes, unlike really any other machine learning solubility paper I could find, who tend to stick to one solvent at a time. Our way, I think this is the way to do it because you get to exploit these triangulation-friendly data points that you've got in your data set. But, of course, to get the best out of it, you need data from the same API that will not always be available. However, I think this stacks up well. And this is with a tiny data set. You could easily extend this in every dimension that I've described, and I don't think we've hit anywhere near the ceiling of performance yet. So hope there may be a round 2 of this, hopefully with more than just me at the helm. But yeah, that's what we've learnt, and 20 seconds left. I'd better shut up. Yeah, thank you very much.
Today I'm going to talk about developing machine learning method to predict mechanical properties. So, we all know molecular crystals are generally brittle, but there are a number of molecular crystals which exhibit mechanical response, which is they respond to external stimuli like heat, light, or chemical or mechanical force and transfer into work. So mechanical responsive molecular crystals can be broadly classified into 2 different types. Molecular crystals that relax with fragmentation, which is they just burst, and the molecular crystals which relax without fragmentation, which in the case is plastic and elastic deforming crystals. Excuse me. So, the mechanical response in molecular crystals is mainly dependent on the crystal packing arrangement of the material. And why is it important? It's important because a number of factors related to manufacturability of the drug is directly related to the mechanical properties like compressibility and things like that. Mechanical response behavior is directly related to crystal packing arrangement. So when we talk about crystal packing arrangement, we have generally what we call as molecular arrangement, and then between the molecular arrangement you have hydrogen bonding interactions. These are strong hydrogen bonding interactions and weak hydrogen bonding interactions. So to develop a machine learning model, we need a data set which consists or captures this information. So for this purpose, what we are using is a method called persistent homology, wherein we represent a crystal structure as a set of barcodes. I will go into details about the method just now. So this is basically starting with the crystal structure of the material that you're working with. Persistence homology is basically an algebraic method wherein it tracks the topological features in the data, meaning what are the connected components within the crystal structure, what are the holes, and what are the graphs within the crystal structure or any data set, and how do they vary over time. So like I said, the starting data set is the atomic coordinates of the crystal structure. And what we do is generally in this method, choose a ball of some arbitrary diameter d around all the points in the crystal structure or around all the points in the atomic coordinates. And then when the balls overlap, you connect them. But what you see here is a graph, basically, which is consisting of two clusters, one above and one below. But whilst this does give some information about the connected components, it doesn't tell us about the how the holes or higher order features in the data set are varying. So for this purpose, we need a more sophisticated method of analyzing the connected components. The way this is done is by building simplicial complexes. Again, there are some set of simple rules in the literature. So all the data points or all the coordinates are basically used as zero simplexes. And when two data points or two coordinates are joined or are intersected, then we call them as one simplex. And similarly, when three data points intersect, then they are called two simplex and three simplex and so on and so forth. A combination of different simplices is called simplicial complex. So coming back to the original data set of crystal structure of fulfanamic acid, I said earlier that we are not able to track the holes by using the earlier method, but whereas if we do plot in the simplicial complexes, what we will be able to do is we will be able to map in the holes, as you can see here, the holes corresponding to the benzene ring and whatever other holes within the data set. But one challenge here is that what is the diameter of the ball that should be used? This is an arbitrary diameter that I was showing you till now. Unfortunately, if the diameter of the ball is very small, as you can see here, not all the points within the data set are connected. So the way this is overcome is using balls of all the diameters and building the simplicial complexes for each of them. Now, again, barcodes is something central to persistent homology. The concept of barcodes is illustrated using a very simple 4 points here. Again, so persistent homology all involves building balls. So when at diameter D1 of the ball, what you see is that the 4 points are connected. So that corresponds to the birth of the barcode, and at diameter D2, the hole, the central hole is filled up. So that corresponds to the death of that particular data set. So again, the barcode is represented as intervals D1 and D2, which correspond to the birth and death. So again, coming back to the original data set of crystal structure of fulfanamic acid. So using this method, basically starting with the balls, size of the balls, you build the simplicial complex, and at the bottom you have the barcodes corresponding to that particular simplicial complex. So at each size of the ball, you have the corresponding simplicial complex and corresponding barcodes. At the end, for all ranges of balls and a range of simplicial complexes, what you get is called a complete barcode of the crystal structure. So what we are doing here is basically tracking the changes in connected components, the holes and graph structures that are within the data set, here in this case, the crystal structure. So what I want to point out here is two examples, 2-chlorobenzoic acid and 2-bromobenzoic acid, the barcodes. They're very similar in terms of crystal packing arrangement, but what we are able to see by this method in persistent homology is that it can capture the small, minute differences between the two crystal structures. So topological fingerprints, so the barcodes basically capture the fingerprint, can be used as a fingerprint for the crystal structures. There are different ways of representing persistent homology. The first one is the barcode. The second one, persistent diagrams. What you're basically doing is you're representing the birth and death on XY plot. And the other one is persistent landscape. Each of these are used for different purposes. Persistent diagrams can be used to compare to persistent barcodes, whereas persistent landscape is generally used for data set containing a huge number of data points. So if you want to, quickly eliminate noise, then it's an easy method to do so. So in this case, what I want to show here is, again, the crystal packing arrangement of 2-bromobenzoic acid. By plotting the persistent barcodes, I've just mapped out the intermolecular interactions. So what I want to show here is that by plotting persistent barcodes, we are able to capture all the molecular and intermolecular interactions in the crystal packing arrangement. Again, flufenamic acid. Just want to highlight the fact that all the molecular and intermolecular interactions are captured. So this is what we want to use as topological descriptors for building a data set of mechanical properties. So when we talk about mechanical properties, if you look at the literature on organic mechanical properties is very little. So we took the route of computational method of calculating elastic constants. Again, the elastic constants themselves come from the very familiar Hooke's law, or generalized form of Hooke's law, where stress is directly proportional to strain, and you have the stiffness tensor or elastic constant tensor. Now, this elastic constant tensor is dependent on the symmetry of the material. So if the crystal system is triclinic, then it is least symmetry. Then you have 21 independent elastic constants. Whereas if it is monoclinic, then the symmetry is higher compared to triclinic. So some of the elastic constants vanish, so on and so forth. So higher the symmetry, the smaller the number of independent elastic constants. So this is helpful in terms of computational time, but most organic compounds are triclinic and monoclinic, so they do tend to take a lot of time to do these calculations. So once you have the elastic constant tensor, different mechanical properties of the material can be calculated, like bulk modulus, shear modulus, or elastic anisotropy, and things like that. And these are the empirical equations, basically. So when I mentioned about computational calculations, so this is the workflow that we use for doing the computational calculations. Basically, we start with the crystal structure from CSD, geometry optimize it, and use the geometry optimized structure. And we apply the constant strain method. All these calculations are done in CASTUP. And calculate the elastic constant tensor. And after that, we have a set of what you call as checks. Mainly, if the errors in the calculated elastic constant tensor are above 15%, so we tend to say leave off the data. And the other thing, other checks are basically you have the tensor and you go about checking the eigenvalues. They have to be positive. And other things relate are Born-Hague stability criteria. So there is a stability criteria. For the materials to be mechanically stable, they have to follow this stability criteria. And we have tested a number of force fields in this case, like a DFT B plus, and and other things that can be done in Material Studio. A number of cases, what we have observed was they don't really, the resulted elastic constant don't really, are not, does not really follow this criteria, or they don't really stand this scrutiny. So Young's modulus, here is the results of the data. What we see is a plot of Young's modulus versus the H bonding distances. These bonding distances were calculated or obtained from the persistent barcodes. As you can see that there is no definite correlation here in this case, which is what one might expect probably. And something similar was reported in the literature recently. Talking about bulk modulus, what you see here is a plot of bulk modulus versus calculated density. Now, as the density increases, you see that the bulk modulus also tends to increase. So what you see here as 0, 1 to 3 is the dimensionality of the crystal structure. So vaguely you can see that 0 is basically discrete molecules. They don't have any hydrogen bonding interactions from molecule to molecule, whereas 1 is the molecules, the crystal packing arrangement has got infinite arrangement of one-dimensional hydrogen bonding arrangements. 2 is two-dimensional, 3 is three-dimensional hydrogen bonding arrangement. So what you see here is that basically as the dimensionality, I mean, again, there's a lot of overlap, but yeah, discrete molecules tend to have low bulk modulus, which I think is important from the point of view of compressibility. So altogether, we built a data set using the intervals calculated from persistent homology and calculated mechanical properties. And these were plugged into the machine learning workflow, wherein you have different learners and to build a machine learning model. So this is what you see, at least for the case of bulk modulus, and for other mechanical properties, the values are really less. So before I conclude, this is the workflow. I think what I've presented here is two pieces. One is the way to represent crystal structures, and the other is calculation of mechanical properties. These two strands are plugged into machine learning workflow to build a machine learning model. So to summarize, persistent homology captures the geometric features in the crystal structures. The barcodes are basically fingerprint of the crystal structure. And what I've probably shown you is the barcode capture both pairwise and many-body interactions within a crystal structure. And this data of barcodes and calculated mechanical properties can be used to build machine learning models. I would like to stress here that we are severely limited by the data of the calculated mechanical properties. But you can still build a machine learning model. Thanks a lot for your patience.